Okay, so let's talk about the first process. Well, first of all, can you do it in large enough quantities? Well, large enough means both in space and in time. How did we get fossil fuels in the first place? At the lowest order, it's very easy. About 300 million years ago, the level of carbon dioxide in the Earth's atmosphere was 10 times what it is today. So we're not talking 400 parts per million. We're talking about 4,000 parts per million. At 4,000 parts per million, trees grow to tremendous sizes. Of course, nobody was there to observe it. When it got buried in the ground, there's no oxygen. Eventually, it touches hot rock, and that heat and the high pressure slowly turns it into coal. You add a little water, you can get oil, and add more heat to become natural gas. So this comes about naturally because you have high temperatures and high pressures. High pressures is hard to get, but we can get even higher temperatures with molten salt. And so I'll talk about how it's possible to do the same thing in 10 minutes. Okay, that's why it's possible to compete and perhaps even beat fossil fuels. Okay, so here's a schematic. Here's a tabletop model that we built. If you'd like to have one, somebody should donate $10,000 and we'll give you one. That's what it costs us to produce. If you'd like to have one, it's wonderful. We call it the crankberry. Everything is named after fruits in our project. So we call it the crankberry. You put biomass in here into a cylinder with holes. You turn a crank. This is at a height that a small child can do it. And it goes over here. It dips into molten salt, which is a eutectic mixture of sodium acetate, potassium acetate. Let it sit for 10 minutes. It's kind of like bad cooking. We're bad cooks. Everything we cook becomes charred, okay? So it turns into charcoal, and now it's very salty, so then we turn the crank some more, dip it in 2 batches of water, take it out. It's charcoal, 10 minutes, okay? And there. So any kind of biomass will do. In Hsinchu, there's a lot of bamboo, so we use bamboo. It's the fastest growing land plant. This is a twilight zone, an invasive species called Lucana. It's all over Southeast Asia. It was introduced by the Japanese. Nobody wants it. It's basically a bush. You can turn this into charcoal. This is a banana peel turned into charcoal. Orange peel, anything, okay? That is organic. You can turn into charcoal in 10 minutes. Now, if you do it at 300 degrees, you get the lowest grade of charcoal. We call that a coal replacement or eco-coal. If you burn that, that becomes carbon neutral as long as you grow back whatever you use this year and next year. Okay, you grow it again. If you go to higher temperature, you get a higher grade of charcoal that we call biochar. That's a very good soil amendment. That becomes carbon negative. And when you heat this up, you expel gases, mostly water vapor, but also a lot of acids, like vinegar, okay? It's acetic acid. In fact, all the acids, because we use acetate salt in the plant that would normally come out, gets turned into acetic acid, okay? And that we can turn by our salt cycle into acetone. If you heat this salt up to too high a temperature, it will decompose into carbonate salt plus acetone, very pure acetone. Now, acetone is not as good as gasoline because it's not a hydrocarbon. It has 3 carbons, some hydrogens, and an oxygen. You need to remove the oxygen to make things as good as hydrocarbons. And this we do in the same way that inside the Earth does it. You add heat to it in the presence of basically a rock that's very porous, a zeolite, in this case a nickel-based zeolite, very good catalyst, and it will expel the 3 oxygens in the form of water, and the rest is C9H12. It's a hydrocarbon called mesitylene. It's right in the middle of what gasoline mixture is, okay? Now, it's not as good as gasoline because gasoline, you need to light it, okay? You need some lighter stuff that has higher vapor pressure, but it's a very good aviation fuel all by itself, okay? So that's one example. There are probably others. And then what you cannot condense comes out as carbon monoxide, hydrogen, plus carbon dioxide and other things. But this is burnable. This used to be called town gas. Today we call this syngas. Okay, so this can replace natural gas. So that's the three kinds of things. You just follow what nature does, and you got what nature gives you, more or less: a solid product, a liquid product, and a gas product. All of them of which are fuels, or good soil amendment. Now, what does this charcoal look like if you were to put it under a scanning electron microscope? Here it is, okay. What you see here are walls. These are the walls of the cells of the plant, okay. So that is maintained. It's just been turned mostly into carbon. At 300 degrees, you see there's still stuff inside the cell walls. At 500 degrees, you see the stuff inside the cell walls have disappeared, become very porous. Now, here's something obvious. All these holes are connected, okay? Because in a plant, every single cell must have access to water, okay? So there are channels that will bring water inside and let it come out. So they're all connected. That's what we mean by porosity. Not only holes, but holes that are connected, okay? Now, there's so many of these holes and cell walls that the so-called BET area, this is Braunauer, Emmett, Teller, Edward Teller of nuclear physics fame, is very high. So 1 gram, you can barely see it, has a surface area about the size maybe of half of this room, 6 meters squared. This is, this room surface area, just 1 gram. All right? That's because it's not just the surface that has it, it's throughout the thing has this walls. So you can already see why this might be a good soil amendment, okay? Especially if you want to hold things like water or you want to filter out poisons, toxins. Now, it's possible to get even higher surface areas, but only by making holes in the cell walls, right? If you make small holes, a few angstroms in size, that's activated carbon, all right? For example, if you add a strong acid to all this before you do it, or a strong base, it's possible to make activated carbon. We did this the very first time, and we got 2,088 meters squared per gram as a bet value, okay? That's the world record is 3,000. All right, in the very first try, we got 2/3 of the world record. Bronze medal, not gold medal, but maybe bronze medal. So it's not difficult to do. Now, why is that important? It's important, imagine, when you don't have clean water. When you have a flood, all the dirty water becomes mixed with the clean water. You need some quick, fast way to filter that water so you don't get any germs. Right? Germs are single-celled organisms. So if I crush this thing, all I have left is the pores in the walls. By definition, those are smaller than single-celled organisms, and so what will pass through is only water molecules. You'll leave behind all the germs, you'll leave behind all the bigger molecules. So this is kind of a rough, quick way of understanding how it's possible to produce different grades of charcoal that are worth, of course, different amounts of money, okay? This might only be worth 10 American cents per kilogram. This might be worth 20, 30, 50. This is worth $1.50, $4. Okay? So it depends how much effort you want to put into. But using the same machine, you can do this. Now, of course, we want to do this at a large, fast scale. So we built this machine. This had to undergo approval by the Committee on Environment and Safety, and Professor Kai Zizong was very helpful in getting us through this process. So you start by melting heating salt in a tank, all right? Now for heat, there could be any heat source. It could be from electricity, it could be from part of the charcoal that you generate itself, or it could be nuclear reactor. For convenience, we use electricity, but as I'll show you, commercial purposes, you want some cheaper source of heat. Then you have a pump. It flings this salt up to a higher level, which is the heater, which, if you want, you can raise the temperature some more. And from there, it can flow down to the rest of the system. Okay? So the first place it flows is into the cooker. So here's a cooker. It has a lid. So you open the lid. You fill a porous basket with biomass. You put it in there. You close the lid. And then you circulate the salt, hot salt through it. It cooks it. And in 10 minutes, you've got charcoal. All right? And in the meantime, it expels gases, which you pass through a condenser. And the condensable portion comes out. And the incondensable portion, the syngas, goes to a burner, which we burn here. In principle, you could generate electricity with this gas. It's a very clean source of heat, and since it's a gas, it's easy to make it coupled to a gas turbine. So, but we haven't done that yet for on-site electricity. Now you've got dirty, salty charcoal, so you have to wash it because the salt is worth more than the charcoal, so you have to recover that salt, and that's done in the sequence of basins. Okay, we have 13 basins here. This is the most salty water from the previous round of washing. So you use this very salty water to wash the salty charcoal. It goes through a filtration system. This very salty water now is saturated with salt, and you send it back into the melter. It expels the water, so you recover the salt. Meanwhile, this one is empty, so then you wash with slightly less salty water. When you're done, you put it back into here, and then this one is empty, you wash. And each round of washing, we go down roughly by a factor of 2. So since we have 12 basins, we go down 2 to the minus 12 of what we started. So, you know, less than 1/10 of 1% of the mass of the charcoal is now in salt. And that kind of level is below the noise, which is that plant matter automatically has salt in it. Okay, so that's how we do it. So you can think of it as salty water is moving up this way, the charcoal is moving this way, and at the end you're washing it with clean water, so it becomes very clean. That's the whole trick. There's some high voltage equipment, etc., that's out there. Okay, let me just quickly convince you that this is economical. So if you made 1 ton of biomass, you subject 1 ton to this process at 300 degrees for 10 minutes, what do you get as products? Well, more than half of it comes out as big pieces and fines plus tar. Okay? Fines means particles too small really to have commercial value, so we would burn that portion or oxidize that portion to use as facility heat. Now the charcoal pieces that you make, I would just state as a blanket, if it's worth making charcoal, it's worth more than your biomass. Otherwise, why would anybody do it, right? So automatically, this is true. It's worth more. So the rest of it must be profit. And because we are condensing it, we are actually able to more than recover our expenditures. So what do we get? Well, mostly you get, of course, water. But next most is acetic acid, all right? Which, as I said, can be turned into mesotylene. It's a simple problem in chemistry to assign, if you have 124 kilograms of this acetic acid, and you have this reaction, how much ends up in mesotylene? It's about this, which is 48 liters of gasoline equivalent or better. Okay, how much does 48 liters cost in Hong Kong? I guarantee you, it's more than the cost of that charcoal, the worth of that charcoal. So our advantage to traditional methods is one, we're hundreds to thousands of times faster than traditional ways of making charcoal, and our product is worth at least twice as much. That's why we think, you know, unless you're a very bad businessman, I am a very bad businessman, so we have to find somebody good at business to do this, but the basics are good, okay? to do this.